Okay, now we'll be beginning with topic 3.1. We'll be talking about the batch reactor. So, characteristic of any type of batch reactor, the reactants are actually initially being charged into a reactor, and the mixture is actually allowed to react for a certain period of time. So we say that it's initially charged into reactor and allowed to react for a certain amount of time. After that, then the content is being discharged. So a typical example of a batch reactor is you have actually done it before. It could be a beaker or it could be a flask that you done in your lab before. So these are some example of a batch reactor. Okay, so in the lab, like mentioned that you have actually done batch reactor a lot of times. They used to investigate the kinetics of chemical reactions. Now, but in commercially they are used as mixing vessel, chemical reactor in pharmaceutical industries, or as fermenter. So they have a following characteristic. Definitely, it's a closed system. So when you say there's a closed system, means that there's no input and output during the course of reaction. So all the reactor, like mentioned earlier, is being charged in the reactor at time 0. So until when the reaction is finished, then we will discharge all the content. And total mass of the batch is fixed because there's no input and output during reaction. So the mass of the reactor will maintain throughout. Volume and density may vary as reaction proceed, especially if you talk about in a gas involving gas phase reaction. So volume and density may vary, but it's not always. Energy level in the reactor may change as well. So energy may vary. So most of the time we will use like a heating or cooling coil to control the temperature if in the reactor. Reaction time for all fluid is the same. So if you talk about like A plus B give you C, the time to react A and the time to react B in the batch reactor, they are the same. Okay, or in other words, yeah, they are the same. And operation of the reactor is unsteady state. This is one of the most important point. So we will actually look at it in topic 4. We talk about other type of reactor. But all in our words and say that this is not a steady state reactor, not a steady state reactor. Okay. So in the ideal, now we use the point ideal batch reactor, composition temperature is uniform at any time, any point of the time. So imagine that this is our reactor. So whether the temperature is at this point or the temperature or concentration at this point, they are all the same, which means say that we assume it is well mixed. Okay, so for constant density system, because remember that initially just now earlier on we mentioned that the density and volume may change. So but now if we consider a batch with just liquid phase reactor and product, so the keyword is must be liquid phase. Total mass of the batch is constant. Okay, just now we say already the mass is constant. If the volume is also constant, I say if the volume is constant, then density is constant. So like I mentioned that if you have a gas phase system, this does not apply. So the rate of disappearance of I, reactant I per unit volume is given by this. Okay, so this is the rate of consumption because there's a negative sign here and there's a negative sign here. So this is per volume, change in mole over change in time. So if you say a constant density, this V over here can be brought into the differential term, and Ni over V is actually equals to concentration. Remember, concentration is mole per unit volume. So this therefore with this we can actually write as change in concentration per unit time. Do note that this is only for constant density system. And the formation of J is follow. This is talking about I change to J. Okay, so the formation of J is change in concentration of J per unit time.